Again, sir, let me start the session.
Okay, sir.
Yes, sir. Just a minute.
Thank you, sir. Once again,
Sir, please wait.
okay.
This is session first day, session one. Session one resource person is Dr. A.G. Karthikeyan, Assistant Professor, Department of Mechatronics Engineering, Reva University, Bangalore. He has more than 10 years, 13 years of experience in the teaching, as well as uh, he has completed his research in the area of additive manufacturing and superalloy materials. So this session is suitable for us to extract the knowledge in the area of challenging in additive manufacturing and superalloys. Uh, I welcome Dr. A.G. Karthikeyan, Assistant Professor, to provide this session. Karthikeyan sir, the session is yours.
Once again, very good evening to one and all present over here, sir. At the outset, I would like to thank the uh, MC team here, our Manivel sir, the MC team here. I would like for the introduction given about me. Then next, I would like to happily congratulate the Dr. Manivel and Prakash team for grabbed the grabbed the Atal fund for 6 days online FDP program on the titled Engineering Materials for Multidiscipline Applications. Then I should also thank the various heads, teams, deans, directors, pro VCs and VCs of Reva University, Bengaluru, and also NPR College of Engineering and Technology, Nattam, Tamil Nadu. Actually, let me introduce shortly. I am Dr. Karthikeyan, Assistant Professor of Mechatronics Engineering, Reva University, Bengaluru. Shall I share my PPT, sir?
Yes, sir. Sure, sir. Please change the presentation also.
Whether my
Yes, sir.
PowerPoint is visible, sir?
Yes, sir. Is it visible?
Okay, here the title, theme of our 6 days online FTB is engineered material for multidiscipline applications. In this, my title is Challenges in Additive Manufacturing of Superalloy Materials. Here, the today's session, we are going to see the content. Here is introduction to the engineered materials about the superalloy materials, because here the theme is given as engineered materials for multidiscipline application. So I have one or two slides I have taken for introduction about the engineering materials, how it's evolved from conventional to nowadays what we are using, how principles are is clearly said, how our world is today's world gets changed, right? Then about our superalloy, that's our core topic here. Then influence of superalloy in turbine, especially I am taking the application of turbine, how it is influencing then conventional manufacturing processes versus additive manufacturing processes. That you know very well that my title is the challenges of additive manufacturing of superalloy material. So how it is varying from conventional manufacturing processes, that we are going to see. Then importance of powder bed fusion additive manufacturing process, that is one of the process of additive manufacturing technique that we will discuss. Then challenges, the main, the theme of the title of my today's presentation is challenges and solution in additive manufacturing of superalloy materials. Then what we have carried out research, that is metal printed, that is superalloy materials in direct metallization print process. That also we are going to. Then finally, what are the research opportunities are there in the additive manufacturing process? Nowadays, the current trend is additive manufacturing process, that is why advanced manufacturing technique. Here, the first one is the introduction to the engineering materials. Here, why materials to be engineered, that is for enhancing their properties, especially physical, chemical, mechanical, other functional properties to meet the demands of diverse applications here, right? Diverse applications in the sense here, initially we have started the material like wood and stone in the ancient period to nowadays to the advanced materials like metallized nanomaterials. One of the progress of these material is revolutionary, right? Then early application relied on simple metals like iron and steel, but today's technology utilizes various functional grade elements, smart materials, biodegradable materials, superalloy materials, composites. In that composite, so many types of composite materials are utilizing for higher performance and specialized utilization, right? Here, the engineering materials are fundamental to the advancements in diverse fields, including aerospace, automobile, biomedical, electronics, and construction. But these materials like metals, polymers, ceramics, alloys, and composites and smart materials are to meet the demands such as strength. Why we have to go for these kind of composites, alloys, superalloy, smart materials, functional graded materials is for to get the strengthen and also for durability and also for lightweight applications. It is much needed in today's industry world, and also thermal or electrical conductivity and so on. Here, the key characteristics of engineered materials are, first of all, why I said that customization. The customization is for various properties to be customized for
Where?
the application is needed, right? Then
Group
advanced
map?
processing. For particular material, how we are going to
In group
process
நீங்க ஆட்
is
ஆகலையா?
very
ஒரு
important
ஆட்
in this,
பண்றியா?
right? For example, to take a polymer based.
வாட்ஸ்அப் குரூப்ல.
Hello, so am I audible?
Yes, sir.
Yes, sir, it's
Continue, sir.
audible, sir.
Okay, okay. Actually, how we are going to customize these kind of what is it properties to get the strength, conductivity, flexibility, corrosion resistance. I didn't list out many. Here you can see that oxidation, then so many wear, then warping, then so many morphology, structural morphology, so many things we need to customize the material. How we can customize these materials with the help of advanced processing techniques, right? Here we are categorized into conventional and non-conventional manufacturing techniques. In conventional, already we have seen so many types of, you know very well that as a mechanical engineer, we know very well that casting, forming, forging, machining. In that machining also, it has so many types like turning, then milling, then conventional turning, milling. So many techniques are there. But here, non-conventional manufacturing, what we are considered here is even in machining also we can consider the non-conventional manufacturing, that is non-traditional machining process also there, like thermal energy processes, laser energy process, electrochemical energy processes. Why these processes are required to customize the material to achieve the user's requirement. Now, without material, you know very well that without material there is no innovation takes place in any applications. It's very well known, right? So how that material to be processed to get the customized, that is what is that, to the user requirement, that is based on the processing only. Here, non-conventional manufacturing, one of the advanced technique we call it as what, additive manufacturing. In that also we can process that material to achieve the respective properties to be improved, right? Here, multifunctionality in the sense, here the structural integrity with electrical conductivity, in the sense what, electrical conductivity, not only we are focusing on thermal conductivity property in any materials, but also we have to concentrate on electrical conductivity. Why? Here automation plays a major role nowadays. So everyone knows very well that automation plays a major role. Automation, how it is works without sensor and transducer, it doesn't work out, right? Here the advancement in the sensors and transducers also plays a major role, right? Advancements like electrical conductivity, how it is gets improved to enhancing the electrical output by the sensors or transducers. That is also we have to concentrate. That we consider as what here, multifunctionality characteristics. Then cross discipline, in the sense here, aerospace, medical, energy, construction, electronics. Here you can see that in the aerospace, starting, I will show you the how the influence of superalloy has been enhanced to enhance the performance characteristics of turbines in aerospace. That I will show you later. Then here, aerospace, what we have to consider, lightweight composites for fuel economy, that we have to consider. Then for medical purpose or medical or biomedical purpose, the biocompatible materials we have to find out, right? The right materials we have to find out. Otherwise, it become what is toxic in nature, right? That to avoid the toxic in nature, we have to find the biocompatible materials for implants and prosthetics, right? That one, that material should not affect the human being. Here, life plays a major role. For whatever the application, we are developing the material with tolerances, but in medical application, we does not provide any instruments or any materials with tolerances, because here human life plays a major role, right? So there you have to consider 100%, that is zero tolerance. We have to concentrate on the materials, right? Then energy, the materials for solar panels nowadays, it's a what is that, electrical vehicle. Then you can consider for Mars related vehicles, right? There land rovers can be utilized there. How it is enhancing the energy with the help of solar, that plays a major role. Their material plays a major role to find the maximum energy withstanding, right? That is energy related. Then electronics and construction related, we know very well that here we can alternate to the construction, alternate to the sand. Here so many materials they are using, that is also engineered material, we call it as processed materials. Then electronics, we have seen sensors, transducer, actuators. For the enhancement of that component, we have to concentrate on engineered materials, right? So overall, here engineered materials, our theme here is what, without that engineered materials, here the innovation cannot be happen in any field, is it? Then engineered materials are the backbone of the innovation, that is transforming ideas into reality across the various discipline, right? Various discipline here is interdiscipline, right? Now I'm going to enter into our topic, right? Here our title is given introduction to the superalloys, right? So many may know about superalloys, many may worked in as a mechanical engineer, many may worked in the superalloy materials. Few may not know, but here I need to here explain about what is that superalloy. Superalloy is a high performance alloy and exhibits excellent strength at high temperature. You have to note the point that high temperature, resistance to the thermal creep deformation, good surface stability, and resistance to the corrosion or oxidation. These are the properties, that is excellent properties, that especially for the higher end application where we are called as rocket engine, turbines, then that we call it as extreme environment. Extreme environment in the sense what? Environment in the sense that is maximum temperature and also maximum pressure to be happen in that environment. There the material to be sustained, then these kind of superalloys only can be sustained because of these excellent properties, right? Now, next question may arise, right? Any high temperature alloys can be called as superalloy. Is it? No, because superalloys have a specific characteristics and also it has a specific features, right? One by one, I will tell you that it has a common features of FCC structure, of matrix phase, that is solid solution strengthening, precipitation strengthening, right? Here, what is that FCC structure? Here I have in the bracket, I have mentioned that Ni, CO and Fe is nothing but nickel based superalloy, cobalt based superalloy and iron based superalloy. Only these three major categories are available in the industries nowadays, right? In these kind of what is that, in these categories only so many researchers are going on, right? Here FCC structure is nothing but, is everybody knows very well that if any metal forms based on the simple cube, that is FCC, that is face centered cube, then body centered cube, how the atom forms in the that material, right? Then HCP, that is hexagonal closely packed, right? But especially that superalloy falls on the FCC structure. What are the unique characteristics or unique features are there in FCC structure? It can withstand high creep resistance, right? High creep resistance, why it is needed? Because here superalloy is going to utilize in higher end application, that is high pressure, high temperature based. So it has to be withstand. So you have to take the FCC structure only, right? Then solid solution strengthening is nothing but here, along with the nickel based or cobalt based, iron based, along with that a few component, that is element has to be added. Based on that, it has been intermetallic formation can be takes place to create a solid strengthening to the, what is that, the common base material, right? Here precipitation strengthening is nothing but the minor element like silicon carbide are used in the nickel based, cobalt based and iron based material. That minor based, that is minor material helps for elements, helps for creating the precipitation strengthening of that whole superalloy material. So therefore, these kind of the very good, excellent, and physical properties and also chemical properties and also, what is that? The structural characteristics of superalloy. It is highly utilized in turbochargers. Then I have highlighted very few. That is land-based gas turbine, rocket engines, chemical and petroleum plants, aircraft turbine engines. Here you can see that here initially after the World War, that our principals have said that after the invention happened after the World War, highly gas goes to the our mechanical, like whatever the types of engines or materials, it goes to the extent level, right? Here you can see that turbochargers, gas turbine, rocket engines, chemical and petroleum plants, there it has been utilized in, what is that, high that is most highly elevated temperature. It can be utilized elevated temperature in the sense, initially it was started with a 650 degrees centigrade and above. Now it is crossed 1800 degrees centigrade and above. That I will tell you in one by one next slides, right? Right, that elevated temperature is more than 650 degree centigrades. Because of these demanding applications, here the superalloy is highly utilized in these kind of applications. Versatility in the sense, here versatility stems from the fact that the combined high strength with good low temperature ductility and excellent surface stability is nothing but, here is, it has so many categories of superalloys. If you take a nickel-based superalloy, it has n number of superalloys are there. If you take cobalt-based, there also so many types are there. If you take iron-based, there also so many types are there. Here, versatility in the sense, it can be fit for any higher applications. Any material, if you take, it can withstand. But durability, that we have to consider based on the particular that material we have to consider for particular applications. Here you can see the nickel-based superalloys. It has inconel, astralloy. If you consider the inconel, it has so many types. Actually, we have done a research on inconel 718, 625, then mnemonic 80A, then monel K500. In the subtractive machining also, and also additive manufacturing also, nowadays we are our ongoing projects are in Monal K500, Inconus 718625, and all. Then cobalt-based superalloy here, ANS Tellai, then HS, then Triballoy, then MAR, and also iron-based superalloy also there. Here, super fer, in the sense fer here means that iron-based superalloy. From that, you can identify that it is comes under the iron-based superalloy. Here, why we call it as nickel-based, why we call it as cobalt, why we call it as iron next thing. Here is what nickel in the sense maximum 50 to 65% nickel composition should be there. Then remaining that what we have seen on solid solution strengthening and the precipitation strengthening, the remaining 4 to 5 components will be 5 elements will be there. Okay, the remaining that is 30 to 35% will be remaining elements for creating a solid strengthening of superalloy and the precipitation strengthening of the superalloy material. Similarly, in the cobalt based also, here cobalt that is 50 to 65, then iron is also 50 to 65, then remaining the 30 to 35 can be utilized. That is, sorry, 35 to 40 can be utilized for remaining elements for solid strengthening and precipitation strengthening of the superalloy materials. Here, why does the nickel-based superalloy highly used in many applications? That is, many applications in the sense here, what I have quoted earlier is that that is turbine-based related, right? Here, because of the it asks throughout the temperature. Here we know very well that the temperature, based on the temperature with respect to time, the material property gets varied because of the melting point of any material. For example, if you take a titanium alloy also, if you give more temperature or medium or saturated temperature, with respect to time, what will happen? The strength gets reduced, right? But only one nickel-based superalloy, it throughout the temperature, it maintains the strength. It maximum 1800 and above degree centigrade. And also, why nickel-based are mostly used in many applications in the sense here, based on many literature we have gone through that here, it doesn't change as the FCC. FCC in the sense what? Crystalline structure. Why we have, why FCC is better for superalloy materials? For high temperature, it does not change as the temperature, it does not change as the strength with respect to time. That is melting point is high, it maintains high, right? And also here, that is ductility is more, right? Ductility create a more. That's why here nickel based is mostly used in many applications. And cobalt based here, cobalt nickel based superalloy here, room temperature HCP, but above 400 degrees centigrade it gives the water. That structure gets vary. Once the crystalline structure gets vary, even iron also, if you see the iron also here 900 to 1400 maintain FCC, but below and above the 400 degrees centigrade, 1400 degrees centigrade, that structure gets vary. If any alloy, if any processing is happened, for example, if you take casting or what is that, any forging or any other machining or any thermal related energy sources is given to make any final component, there it has to be withstand the temperature to convert as the final product, what the profile we are given, right? If it is the changing the structure is happen, definitely there what is that deformation occur, and also it has the microstructural characteristics will be very poor. Okay, that's why here nickel based superalloys are preferring for so many higher end applications, that is turbine blades, then turbochargers, engines, everything. Here FCC is, why I have here one more, the characteristics is creep resistance is very high. That is FCC is more closely packed structure, right? Here diffusibility are very low, and also it maintains the creep resistance, right? Creep resistance is one of the peculiar characteristics of any higher end application, that is turbine blades or high speed engines and what is that? Those kind of applications here, creep resistance is very important, right? Then Tungsten is also have a high melting point temperature, but it doesn't used in any of the superalloy material. If you can go through that types of the material, why? Because it is BCC structure. Here, if it is a BCC structure, the creep resistance is very low. Even though tungsten has a very high melting point range, but it falls under the BCC structure, but it doesn't withstand the creep resistance. So here it is avoidable in, you can see the tungsten never used in any of the superalloy materials. Here one of the application I have taken that gas turbine engine, here Rolls-Royce Trent 800, that is the model of the gas. Here you can see that so many metal elements are used in the turbine components. Not it is made by fully single material, titanium alloy steel, steels, composites, aluminum, and the final, the last, the combustion chamber and the inlet temperature to the exhaust, inlet and the exhaust temperature. That is there the material is superalloy materials. Why? Because of that, it has to be here. High temperature has been produced and also high pressure has been created. Otherwise, it will get vaporized, right? The material gets vaporized. To overcome that, the superalloy is introduced. One beautiful here, how the influence of superalloy has been taken place in the gas turbine. This one is after the World War. The gas turbine is high-speed engine is developed by various German, like US or various developed countries. After that, after 1960s to here 1998, I was quoted, and I will show you that up to 2000 to and above how it is happened. Here you can see that initially it is started with 900, inlet temperature is 900, then at slowly improved, that is based on the material changes takes place in the inlet, that is component, inlet turbine inlet component. So it up to 2000, that is 1998, 1425 degrees centigrade is maintained from the what 900 to 1425. Here you can see the variation. How the pressure ratio varies from 10.5 to 23. Here exhaust temperature is 427 to 593. This one is water. These changes are incredible. That is based on only materials takes place only. Here you can see the power rating, how it is improved from 50 to 60 to 165 to 280. Then here efficiency, how does it gets improved from 29 to 39, 43 to 58. These are all only happened because of the superalloy or materials are introduced. That is versatile of superalloy materials are introduced in gas turbine engine. Here you can see that the initial why 900 degree, that is also I will show you that here the inlet temperature initially it is started with route alloys. That route alloys gives you what cast iron like steel alloys. So that 900 to 1050 degrees centigrade only maximum temperature. But you can consider up to 2000 and still here only 1400. Now 1800 degrees centigrade and above is utilized only because of nickel based superalloy. Here you can see that how the material influences of the performance of uh, performance of the gas turbine engine. This is only one of the applications I have shown you. These data I have taken from various literatures. Only one of the applications I have shown you. You can imagine that how the world now it is changed based on the materials. What we are telling about smart materials, biocompatible materials, like functional graded materials. Functional graded materials, you know very well that with respect to time it gets vary. With respect to time, actually it gets vary. It gets vary in the properties, right? So here you can see that this superalloys we have to process it to get the what is that final component, right? Whether it is possible, it is high temperature, it has to be withstand high melting point, it has to be withstand high temperature, it has a high melting point property. So we have to process these materials to get the final component. It is very difficult in the conventional manufacturing process. Now how our hero, that is that additive manufacturing is introduced to the superalloy manufacturing of superalloy materials. Here you can see that conventional manufacturing process, we know very well that so many casting, forging, forming, machining. Machining is conventional machining. So many materials manufacturing conventional processes are there. Here you can see that n number of processes are required to convert any final component. For example, if you take a final turbine shape component we have to manufacture, if you do it in the conventional manufacturing, that it has an intricate and complex shapes that is very, very difficult to manufacture in the casting. Even though if you developed, but we have to come across these kind of processes to get the final product. Here you can see that it has the so many limitations and also drawbacks in the conventional manufacturing process. For example, if you get the product from the casting, then directly it cannot be utilized for the applications, right? Then it has to be processed, then it has to be shaping, then it has to be grinding or polishing, or what is it, etching process has been done. Then again sometimes it needs welding or bracing or some other joining process is required. So you can see that for getting a one component, how many number of process we are gone through in the conventional manufacturing. That's why we are utilizing now. We can see that only two steps you can see it in the additive manufacturing process. That only powder based metal. That I will show you different types of additive manufacturing processes. I will show you what in that additive manufacturing process, which process is suitable for the superalloy. That is also I will show you here. You can see that the powder form of component is needed. Then that can be with the help of any thermal or electron beam energy, or that is thermal energies like laser beam or electron beam energy. It can be converted as the final part, right? Sometimes it requires the post processing, sometimes it doesn't require the post processing based on the machine's capability, right? That I will show you. Here, conventional, what are the drawbacks are there in the conventional drawbacks and limitations are there in conventional manufacturing of, especially I have taken the superalloy materials, right? If it is machining, if everybody knows that what are the drawbacks here, machining means we need a special tool for, because already it is a high strength materials, but to convert this as to the any final component, we need a special tools are required, right? So there the tool costs also gets increased, and also you know very well that because of any thermal energy process only, here the removal of material has to be happen. Based on that only, here final part going to get, right? So here that thermal energy is happened, then that impression has to be, the tool material impression has to be happen in the should be fall on the workpiece material also. That is also, that can be, you can see in the edex. I didn't show you here any edex results, only sim results I have shown you, machining sim results of nickel based superalloy here. So that here that material, that tool material impression also fall on the workpiece material. That affects the property of the material, microstructural property of the material. Once it is gets disturbed, then the final component also, that accuracy and precision also gets varied, right? Here you can see that so many notching wear, edge deformation, chipping wear, micro breakout grade. These are the machining, especially machining deformation takes place. Why? Because of the tool materials, these things can be happen. Even though if you if it is non-contact type machining, if you introduced, for example, here machining, okay, sir, you may ask that the machining here for conventional machining, the tool impression may be happened. But if you use any non-contact type, for example, if you take a wire EDM or EDM, there also, if it is non-contact between the tool and the workpiece, but the thermal energy or laser beam or any that thermal energy can be, because of that thermal energy influences there, the residual stresses happen in the workpiece material that affect the microstructure property of the component, right? Here next, casting process. As we all know very well that casting, how it is the process, because we are a mechanical engineer, everybody knows very well that here casting, here that we have to concentrate on pouring of the molten metal is very important. Same way here, how the tool material is required in the machining. Here you know very well that if you want to made any component in the casting, there the dies and molds are required, right? Then again the pattern is needed, right? There also you have to create to withstand the higher temperature material like superalloy. To with respect to that superalloy, you have to create the, what is that, a pattern die material, is it? So that is also tedious. That is also create a cost effective, more that economically it is not feasible. It's more cost effective. Then that the casting, the improper pouring of that molten metal creates the more dendrites on that material, and more porosity has been occur in the conventional manufacturing techniques. Here, low machinability. Machinability, what is meant by machinability here? The machining of materials, while machining of materials, so many processes can be taken place. Many types are there. Here, we know very well that if it is the higher melting point temperature, the higher thermal energy is needed. If it is higher thermal energy is needed, there the energy consumption will be more. If the energy consumption will be more, the power usage is also gets more. So here the machinability gets reduced. Okay, so that's why here the machinability of superalloy is it has the low machinability characteristics when compared with other normal iron or any other cast iron or any other materials. Similarly, here forging also, so many craters, or here it is a conventional process. The proper the force, if it is not applied here, what will happen here? The granular structure variation can be takes place in the superalloy. Here, so many cracks can be, debris can be occur. This is also here, and we have to give the process to get the fine microstructure. This is also one of the drawbacks. Here, point wise, I have given high tool wear. Already, we have discussed that it is a special tool is required for superalloy material. So, tool wear will be higher. Then, high energy consumption because of lower machinability. High energy consumption is there. Residual stresses due to the thermal energy or laser beam or any other, for example, electrochemical, whatever abrasive jet machining, whatever the machining process you can utilize, there it produces the residual stresses. Even the residual stresses happen in the casting process also, then forging process also. Then microstructural degradation, it is happened because of the improper the pouring of the molten metal in the casting, and also improper setting of the parameters in the machining process. That is also create the microstructural degradation, that is also affected. Surface integrity also affects. Then once the surface machining, again one more process, the grinding process is required. Even though if it is done in the any machining process, there grinding polishing also required to create the microstructural degradation, to avoid the microstructural degradation. High material wastages, that is obviously here conventional manufacturing process, it has come across so many processes there. If you take a superalloy materials, here it is highly costlier one. Here if you take any bar, or for example if you want to machine in any machining process, you want to take it as a rectangular bar, or you have to take it in the circular shaft, that is also that raw materials have to many to convert in the profile, it creates so many wastages. Then again lower machinability in the machine, it is especially in the machining process. High strength superalloy, high strength and high toughness materials like nickel based superalloy, cobalt based superalloy, or iron based superalloy, it create a lower machinability in the non-traditional machining process, as well as in the machining conventional machining process is very difficult, very difficult. It is not possible also. Tool gets break, but non-traditional can be happen. There low machinability can be occur. Limited design flexibility here in all the conventional manufacturing process, it is very difficult to create a complex or intricate shapes like curvature shapes of any profile, but it can be happen in the additive manufacturing process, that I will show you, because it has the additive manufacturing process, whatever the types you can take it there, the 3D model will be converted into the final component. Size and weight limitation based on the material specification of machining or forging or any component, there the size and weight limitations are there. Whereas in additive manufacturing, there only powder we are going to concentrate to convert as the final product. So the weight and the size limitations are not required in the additive manufacturing process. Whereas in the any conventional manufacturing process, it has to be concentrate. Difficulty joining, if you consider the welding process, conventional welding process is very difficult and not possible in for superalloy material. But you can do it in the what is that advanced, that is non-conventional welding process. There joining can be happened, but the accuracy will be very less. Again, it required some more shaping process to convert the final product. That is also drawbacks and limitations. Then environmental and safety concerns here, it all happened in the open environment. Then that contamination of the, what is that, contamination of the environment. If the environment is contaminated, that the quality also affects, and also it is not, sometimes the accident may occur to the laborers also, those who are working in casting or forging or any other process. But it is not happen in the additive manufacturing, because additive manufacturing process fully closed process, that I will show you. Finally, cost estimation. Anyhow, the process are increased and also material wastages are there. It creates a more economically, it is not feasible. But even additive also, it has the initial setup is higher, but the process is less. We can get the n number of product that bulk manufacturing can be done, but it takes the time period also. We have to concern about the processes. So to overcome all those drawbacks and limitations in conventional manufacturing methods, we have to move on to the additive manufacturing process, especially for the superalloy material. In this process, everybody knows very well that I no need to give much time on this. Here, layer by layer of the powder formation can be takes place. Then any process, any thermal process or any laser helps, any thermal process with the help of laser or beam, electron beam, or binding of any sheet by sheet, or any other fusion deposition processing. Like that, the process gets vary based on that. Here, the layer by layer, the formation can be takes place. Joining of metal can be takes place. That's here you can see that it can done with the help of 3D model directly. It can 3D model will be converted as the final product. Here you no need to go for any special patterns or dies or molds or any tool materials are required for this process. That's why here it is feasible one. Here, various types of additive manufacturing process are there. Here you can see that binder jetting, direct energy deposition, material extrusion, then powder bed fusion, sheet lamination, vat polymerization. I no need to concentrate on all, but here our superalloy, we have to manufacture the challenges of additive manufacturing of superalloy material. So here we are going to see the powder bed fusion only. Here, superalloys can be built with the help of only powder bed fusion method only, not all other methods. Here you can see that other material extrusion, you can see that polymer related materials you can utilize, thermoplastic materials can be has been taken for the solid film material, and that can be converted as the final part as layer by layer by fusion deposition modeling method. But here powder bed fusion, here the powder, the final, the product to be developed, that is if it is the metal product to be developed, here the powder bed fusion, the metal powder can be taken as the raw material, and any energy sources can be utilized for converting as the molten metal of the powder, and it can be fused together to form the final part. That's the process here. But in that powder bed fusion also, so many types are there. There, which one is better one for the superalloy? That is also I will show you. Here steps involved, as everybody knows very well that for this one is common to all the additive manufacturing processes. Initially, we have to develop any 3D model for our profile. Then it has to be converted into .stl format. This is a machine language, that is .stl format. Then we have to slicing that profile, that is slicing that profile in the slicing software, especially for it might be vary for all the types of additive manufacturing process. It has the open source software is also available for slicing the profile. Then slicing is nothing but it's a simple, the term slicing in additive is nothing but here is simple concept that converting that profile into the build platform area. For example, if the build platform area is 200 mm, and 80 mm thickness, means it will, the 3D model will be converted into that profile only. Okay. Then next support generation is nothing but few that is a few that complex or intricate shapes required a support, that is curvature like structure requires supports. So it can be removed in the post processing process also. Here post processing operation is not required for all the components. Few components may required, that I will tell you. Here, why powder bed fusion is suitable for superlight? The next thing is here, it is high precision and mechanical properties, in the sense here a material versatility, complex geometry, controlled microstructure. Here, these are the main key concepts of powder bed fusions for suitable for superalloy materials. Here you can see that high precision mechanical properties, in the sense whatever the material of superalloy material, either nickel based or cobalt based or any iron based material. Here only thermal energy, or that is thermal energy like laser beam or electron beam, only two sources can be utilized to convert that powder as molten part and get the final part layer by layer, right? Here only two sources can be utilized. We have to, here you can concentrate on two, that is laser beam and electron beam, that's enough. When compared with conventional, you have to concentrate so many processes. But here, once it is filled in the vacuum or any bed, here you can concentrate on laser beam or electron beam, that's enough. Material versatility, in the sense here, all the types of material you can utilize, only energy source you have to vary. That laser beam and electron beam, that is intensity of the laser and electron beam must be vary. You no need to give the additional setups for any if new material is added. That is the material versatility, in the sense any type of material can be built. And then complex geometry, here you no need to create any special patterns or dies or anything here. That's what already discussed. Here complex geometry, directly the 3D model what you are given, the .stl format is given, that G code encode feed into the any types of additive manufacturing process machine, that will convert as the directly that laser or that electron beam movement has been happened to create the complex geometries. But controlled microstructure is happened in the additive manufacturing. Why and how? It is nothing but here, if you concentrate on the laser beam and electron beam, how it is fall on the material, that is powder material, that you can concentrate whether it is openly to all the layers, or it is in that layer it has the distance covered, how much it is distance covered, that can be concentrated to control the microstructure of the final part. Here it has the powder bed fusion has so many types. It has a direct metal laser melting, direct metal laser sintering, selective laser sintering, electron beam melting, direct metal laser melting. Here selective laser melting. Here selective heat sintering. Here you can see that laser and electron, and also laser and electron as the source material that we have discussed, right? But here why it has a different types? Why it has so many types? You may arise it has arise the questions that here you can see that melting and sintering. That difference, if you identify, you can easily get the process of the any types of metal additive manufacturing process, right? Here, if it is melting, here the powder it is fall on the bed chamber, it is by the laser source or by the electron beam, it will completely melt and it become a semi molten material, and it will curing, that is solidified and become a final part. That is the melting process. But sintering is nothing but it doesn't melt the powder completely, but it is partially melt the powder, and it is fused with the another powder. That will be happen in the sintering process. This is the difference between the process of sintering and the melting of any that is these types of additive manufacturing, metal additive, especially metal additive manufacturing processes. Here we have to concentrate on, in powder bed fusion process, we have to concentrate on the process parameters. It has various process parameters. Here laser beam, already I told that it has only two sources. So far it is utilized in so many industries, right? Laser and electron beam. So here you have to concentrate on laser beam, laser or electron beam power, then scan speed, then spot speed or beam diameter, then layer thickness, hatch spacing, energy density. These are the process parameter which influences the performance. Here what we talk about the performance, After I build the product from the metal additive manufacturing process, I have built the super nickel based superalloy. I have taken the powder. I have built in the metal additive manufacturing process. Here, the powder bed fusion is I have utilized either sintering or electron beam. Here, you have to concentrate on these parameters, then only the output, that is nothing but the mechanical property. For example, if it is tensile strength, if you properly maintaining the laser beam or electron beam and also the intensity level of the sources, then only it will forms the layer as homogeneous. Otherwise, here, if it is a layer by layer process. You can imagine that if first layer is completely melt and it becomes solidified, and then only the second layer the powder has to be filled, then that should be completely solidified. That just imagine that if first layer is not completely solidified, before that you have poured the powder, then the microstructure characteristics will be defect. It will create the defect in that. If it is created a defect, then what will happen if the microstructure is not properly maintained, that is, if not properly built, then what will happen? Obviously, it will affect the mechanical property of the material, right? Of any component what you are made by the superalloy material. Here, environmental and machine parameter here, inert gas flow, build chamber temperature, cooling rate. Cooling rate is nothing but the first layer should be sudden cooling rate is also gives the water few drawbacks that I will show you. What are the challenges and solution that I will show you one by one. Here, these are the parameter we should concentrate. Otherwise, here the microstructure of the build the component will be affected. Powder related, for example, if you consider the powder itself defect, the powder itself it has some defect. Initially, it has taken. But one more thing I will tell you that here the powder, the range of powder should be 15 micrometer to the 50, that is 50 micrometer range must be required for converting the final component of any metal component in the respective whatever the types you have seen, right? So you consider that if the 15 or 15 micrometer I have taken, initial lower that is 15 micrometer I have taken. If in that micrometer range if of powder, if any defect is occur while converting that powder, is also what will happen there, also the defects may occur, right? The flowability is nothing but the powder range, that is the minimum size, the flowability will be higher, and also maximum size, minimum size, the flowability will be a lower, and maximum size of the powder. For example, to take 35 micrometer range, that flowability will be more. Then powder absorbability, powder material composition, the based on that material composition, how it is affect the microstructural characteristics and also property of the material. This is also we have to concentrate. The next one, scanning strategy parameters. Here, scan pattern, then scan rotation angle, scan order, then preheating temperature. These are the parameters which helps for. These are the parameters which helps for pizza. These are the parameters which help for improving the final component of the final metal component of the any material powder, right? For example, here I have considered the superalloy, but any metal powder is affordable for these kind of powder bed fusion process. Here, why EBM is the best for among all those the type of laser and laser types also there, electron beam types also there. Why EBM is the best for the superalloy materials? Here it is worked under the vacuum. As everybody knows very well that if it is happen in the vacuum chamber, the acceleration due to gravity is constant. Therefore, it doesn't affect the process. That's why vacuum gives the better and precise and accurate outcome. Then precise energy control. Here you can control the electron beam range, that can be controlled when compared with the laser. Electron beam range is higher. That's why here it is also suitable for superalloy, high strength superalloy material. Then higher material density. Then fewer post processing only needed for if the component is made in the electron beam melting process. Here next the challenges. What are the challenges are occur in that superalloy material, additive manufacturing process of superalloy materials, and also what are the solution can be taken. Here, high residual stresses and distortion. It is one of the challenges happen in the additive manufacturing process of superalloys. Here, why it is occur here? Here you can see that rapid heating and rapid cooling. If the beam range is higher, for example, laser and electron beam range is more, here it leads to thermal gradients and residual stresses. So that the controlling of that laser beam should be needed. Then only here, what is that? You can get the fine microstructural component. So what is the solution for overcome these issues? Here, the preheating the build plate. We no need to give the more energy source. Here, the build plate itself can be given the temperature before the process gets starts. Then that helps for using the energy sources like laser and electron beam, right? Then post-processing treatment. Here, post-processing sometimes it requires the heat treatments, aging or aging is required. That is, heat treatments is required to make the fine reduce the thermal gradients and residual stresses. Then optimized scan strategies in the sense here, it should be optimum levels of scanning strategies should be used. Then next challenges, the cracking. Cracking, how does it occurs? Already I told that here high solidification rates, it is creates the cracking in that. What is the solution for that cracking here? Here you can see that the cracking defects of occurred on the superalloy material. This is because of the higher solidification rate, in the sense cooling rate. For first layer, it should not be solidified later. It is also have maintained the that saturated time to has to be maintained. Then only here the cracks to be avoided. Then here the solutions are alloy modification. If it is occur more crack in that material, it has n number of superalloys are there. So from there you can take the optimized, that is optimal characteristic superalloy can be taken for particular application. Then controlled cooling rates are needed. Then powder quality control, that I already told that what type of the size of the powder has to be taken. That is also affects the quality. Minimum size and maximum size, that flowability also occur. Based on that, the property that the size of the powder also to be taken. Post processing here, same here. Heat treatments are needed. Different types of post processing are there. That is thermal, non-thermal post processing. Then machining is one of the post processing. Machining here, I will show you our work that after build the component in the build plate, it cannot be easily taken as like the polymer based additive product. Here, final product. Here, it has to be processed. That is, any tool that is any non-traditional machining is, that is wire cut TDM is required for final component to be removed from the build plate of the additive manufacturing process. There also you have to concentrate the process of the non-traditional process. Then only the surface of the the final component can be should be maintained. The next one, porosity. Porosity, how it is occurs here, the melting of powder. Melting of powder leads to lack of fusion porosity. Then the gases, what the environment it is used, based on that also it creates a gas porosity. To avoid that, what are the things we have to do? Here, optimizing the process parameters is very much needed. That is, you have to whatever the density of the sources, then scanning strategies, then the inert gases, we have to clean it properly. So everything before before the powder should be added in the chamber, it should be cleaned properly. Then that is also affects the property, right? Then post processing here, HIP is nothing but hot isostatic pressing. That is called one of the post processing for getting the, to avoid the porosity, that is granular formation should be more when we are doing the post processing. Hot isostatic post processing has been taken place in that. Superlight material. Here you can see the reference of where it has been taken, right? Here, the segregation and the non-uniform structure. Why it is happened? Why the segregation is non-uniform is one of the challenges. Why it is happened, and how can you avoid for the superalloy formation, right? Here, high cooling rates in additive manufacturing process, it results in micro segregation of alloying elements, and also non-uniform heating causes anisotropic grain structure. We know very well that if it is anisotropic here, the uniformity is not there, completely is not there. It is happened because of heating causes, that is residual stresses happen, right? So to overcome that, we have to concept. Here you can see that how it structure varies, right? Here you can see the same microstructure of nickel based superalloy material done on the selective laser melting, right? Here how the how does the that process parameter affects the grain structure, and also the micro segregation formation takes place, right? You can see that here. What is the solution here? The same thing here, thermal post processing is needed, and also optimize the process design to be needed. Material development in the sense here, the segregation non-uniform, but that is material versatility. That is what type of one. If the material is not properly affordable for a particular application, then there the list out of a number of superalloys. There you can take the newer material. There you can optimize the process parameter, and you can find the better microstructure characteristics. Next main thing is oxidation and contamination. Oxidation and contamination, because here high turbine engine, then here in the underwater, seawater, then chemical plants, then so many high-end applications here the superalloys are utilizing. There it should not be contaminated, right? It should not be oxidized, and also it should not be corroded, right? Why it is happening here? The higher the processing temperature in superalloy makes them prone to oxidation in the presence of atmospheric oxygen, right? Environmental, right? Based on the environmental. Then here the powder contamination from the handling of storage of the material properties. Initially, starting the process in any metal additive manufacturing process, it should be the chamber should be completely clean, right? Then only the powder should be filled out, and also the process should be started. Otherwise, that you know very well that corrosion how it is happen. Even the edge, any pinpoint of any metal is corroded, it will corrode the entire component. Corrosion is the actually in additive manufacturing of any superalloys, in corrosion is one of the major topic. You can, it is like an ocean, so many things can be explored in this, that I will, if it is possible, that I will take in a separate session, right? Then here the solution, here you can see that in environment, like how it is gets varying chloride or vanadium, how it is gets corroded, that superalloy material. What are the solutions are is required? Inert gas atmosphere. What already I told that atmosphere inside the chamber should be properly maintained. Then powder handling, it should not be bad, and you may see that while handling the manpower, while handling the powder, they may use the gloves and everything, and then only they can use one what is that component to fill it in the chamber. Okay, they do not in the bare end, they do not fill it bare end, they usually not touch the powder also. It will affect the it will create the contamination, right? Then surface cleaning, that's what the powder should be completely fine, and then only it is also gives the better surface stability of the component. Otherwise it is also corroded. Then poor surface finish. Why it is occur the poor surface finish? The layer by layer deposition results in rough surface roughness. Actually, you may know if somebody, if you touch the after printing the component, you may, if you touch it, either it doesn't give the better surface finish. It always gives the rough, because here the scanning of that layer by layer, the scanning is also gets vary. Based on that, also it doesn't give the good surface finish component. Here roughness occur. So to overcome this roughness, a beautiful, that is a solution is that post processing of machining can be utilized. That is wire-EDM can be installed. Wire-EDM can be introduced to avoid the poor surface finish. That's a bigger concept here. that is how to maintain the, if you consider the wire EDM, that spark is there, the wire is also 0.3 it has been taken. Then if the spark is generated, that is also 0.3 if you calculatively, mathematically, if you calculate, you will get nearly below 1 micrometer range of surface finish when you done the machining in the wire EDM. But actually it doesn't happen there. Also you have to monitor the process parameter to get the surface better surface finish below 1 micrometer range. High production cost, obviously the powder is more expensive. If it is more expensive, then here the, what is the solution here? Powder recycling should be happen, then process optimization, that is exact what is the uh, exact that process levels, parameters levels to be identified by various statistical techniques. Thereby you can directly utilize the set the levels to get the final what is that, a precise final product without any wastage of material. Alternate alloys, obviously if it is any costlier, we may have a number of super alloys, right? In that it has the any one can be taken based on the availability. That's the mean here, alternate super alloys. Then the final thing here is the research opportunities. What are the research opportunities? I told that the power process parameters optimization of process parameters plays a major role here. Optimization of process parameters, it affects the final performance of what is that, microstructure, mechanical properties and everything. So here so many optimization techniques are there nowadays. We may utilizing the hybrid optimization techniques, then ANN, machine learning, so many techniques are utilizing. Anyone can be implement to get the optimized process parameters for particular superalloy materials. Then it has to be predicted and it has to be given to the manufacturer for future reference, right? That process parameter optimization. Powder production recyclability, that's a major main what is that concept here. Not only the powder recyclability, here if the rejection happen in additive process, so many are not even considering this for what is that that scrapping for next recycling process. That is also one of the major, what is that, it has the major opportunity to concentrate on the rejected component to how it is convert as the recycle to get the convert as the, what is that, to get the final product, right? Here thermal and residual stress management. Here for finding the any monitoring systems can be implemented to any advanced additive manufacturing processes while the printing. Through that, the way how the thermal resources can be happen, that is also can be management, that is also can be implemented here. Advanced monitoring and control, that is laser beam and electron beam, that is sources, only two sources are utilizing. How it is controlled, right? Only controlling of these two thermal sources, then only the output can be improved, that is microstructure and other properties can be improved, right? Then sustainability and life cycle analysis, that is here. Sustainability, obviously we have to move on to the advanced techniques, right? Here additive manufacturing is one of the sustainable manufacturing methods here when compared with non-conventional machine manufacturing methods. Then application specific research, in the sense what particular, for example, if you take a turbine, already we have discussed about the turbine, right? That how the material influences takes place to enhancing the so many what is that performances, that only one material how it is improves the performances. Like that you have to concentrate. For if you take a turbine, you can you can compare with 2 to 3 number of more number of superalloys, and which one gives the better, that specific research can be taken place to give the manufacturers to find the better superalloys for specific application that can be identified, right? Then microstructure and mechanical properties here, how it is concentrate all those parameters, what are the powder characteristics, process parameters of the machines, then in the inert gas related, what are the specific gases to be used. Then these are the process scanning strategies. Everything should be monitored for particular material, particular superalloy, to get the better microstructure and mechanical properties characteristics, right? Then post-processing and surface engineering. Here post-processing, so many post-processing we have discussed. After built the metal product from the additive manufacture, any laser beam or electron beam of any superalloy materials. Here, based on the property needed, based on the which property we have to enhance, based on that we have to move on to the post-processing techniques, like whether machining is needed for getting the surface stability, or any heat treatment is needed for improving the microstructure. Like that, we have to concentrate on particular post-processing techniques. Surface engineering is nothing but here coating is also possible. Like so many were expertise in coating also, right? In mechanical people in coating is also one of the domain, right? Here are some applications here. Coating is also HVOF coating is also needed, right? So thereby improving the surface integrity of any component, right? Surface stability can be improved. Then here, these are the research opportunities are in additive manufacturing of especially superalloy materials, right? Here the research work what we have carried out in direct metal laser sintering. Here we have taken the powder of 22 micrometer range. Then this is the same image of the that powder what you have taken. This one already published in Q2 journal, recently published in Q2 journal. Here, I know that here already we have discussed that. What is that? Here CAD model. CAD model we have to convert. Here we have concentrated. We authors were concentrated on tensile properties, then wear properties and microstructural characteristics. Right. Here, ASTM standard is taken for the tensile and wear component. That is here based on this ASTM standard, any SolidWorks or any Creo we can convert as the model. Then after converting, this has to be converted as a .stl format. Here, what is our objective here is the process parameter has been optimized to get the better output, that is tensile strength, surface roughness, and better microstructure that we have concentrate. Only three we have concentrate here, but still so many opportunities to improve the process parameters levels, and also output characteristics. Right here, we have implemented the Takuji. Here, only two we have considered, that is what is that? That is tensile strength and surface roughness we have concentrate. So here Takuji we have taken. It is robust design. Everybody knows very well that about Takuji. Here it gives the L9 orthogonal. Here we have conducted the experiment in the direct metal laser sintering, which is available in rapid DMLS, that is Intech DMLS Private Limited in Bangalore. This model is EOS M280 DMLS machine. In this, you can see that the vacuum chamber, how it is how the expertise as utilizing the vacuum chamber with the help of gloves, and it has some components to fill the powder, metal powder. Here you can see the 9 tensile components. That is, you can in the display unit it can be visible. Here, as per the ASTM standards, it has been built here direct metal laser sintering. Here, you can see that the 9 components of tensile as well as the wear has been built. Wear samples has been built. Then, post-processing, obviously here, wire EDM is used. Here, Electronica EcoCat wire cut EDM is utilized. Here, this micrometer range is 1 micrometer. 1 micrometer surface finish can be done. How it is can be done? By setting of proper process parameters. Also have a process parameters, that is pulse on time, pulse off time, gap voltage we have to maintain, then wire feed rate we have to maintain. Okay, properly we have to maintain. Here brass wire is used, uncoated brass wire is used here. Here it has been, here you can see that in the right hand side you can see that the build additive manufacturer build tensile component and the wear component, it cannot be directly taken from the build area. Here it is wire EDM is utilized to remove that metal component. Right here you can see that before tensile and after tensile how it is taken place the tensile test. Here universal testing machine can be utilized. Nowadays the what is that, advanced UTS machines are there. It can give, if you set the load, maximum load, it can be gives the final what is that load per with respect to load, what is the stress strain curve that can be given. Based on that, it can be displayed in the digital that is UTS machine itself. Right here, one surface machine, one of the profile we have taken. This one is taken by the roughness tester machine. Here you can see that what is the profile has been, the evaluation profile has been taken place in the, that is Monal K500 Superalloy material. Here the DOE is done. After DOE, here samples are taken. After the samples, the output has been measured. UTS, that is ultimate tensile strength. Here it's common to, as everybody knows that it is common, SN ratio, signal to noise ratio. We have conducted. It's only one first work we have conducted, like what is that DOE based in the metal additive manufacturing techniques. But so far it has been done in so many conventional and non-conventional machining techniques. Here we have conducted. Here you can see that the optimized parameter has been taken here. What is it? LP, laser power, hatch distance, layer thickness, everything is here. SS scan speed, hatch distance, everything is for what is that? Optimized parameters for process parameter levels for ultimate tensile strength and surface roughness. Right here, contour plot is nothing but how the interaction has been happened. How the within 5 minutes I will complete, sir. How the interaction has been happen for the output, that is tensile strength and surface roughness, that we have taken by the contour plot. Here you can see the conformity. Why we have to conformity here? Out of the 9 experiments, the process parameter, that is optimized process parameter, is not in that level. Due to the SN ratio, it has been obtained, observed, and it has been conducted. It has been conducted the conformity test as per the initial what we have done. The same model has been created and the initial setup has been done in the DMLS machine. The same metal powder has been taken. Then based on that, here tensile strength and surface roughness has been calculated. Here you can see that this optimized parameter improves the what is that output characteristics, right, or performance characteristics. We used to call it as performance characteristics, and improved. Here you can see that here I have taken only 9 levels. We have taken only nine levels. Out of 9 levels, we have improved. Once it is completely thoroughly, if the parameters have been taken into an account to optimize, then we can find the better maximum performance characteristics of any superalloy material. Right here, you can see that the variations for actually in surface roughness value, minimum and maximum level sample has been taken for surface roughness, and also optimized value is taken for the samples is taken for the what is that SEM analysis. There, optimized value gives the better microstructural results. These are recently what we have published in additive manufacturing processes, both metal additive and polymer additive. Now, recently we have published that PEAK material is from the FDM process that we have published in the Q1 journal. So these are the recent publications. Then these are the glimpse of components, that is same what the DMLS machine we have gone. Actually, this DMLS machine available at the Bengaluru, right? Here we call it as the Rapid DMLS. The company name is Rapid DMLS or Intech DMLS, right? Here these are the components, especially they are designing for what is it? Space components. They are space and defense, Indian space and defense. They are developing the components in additive manufacturing, right? That's it. Up to my presentation is gets over, sir. Then, if any queries related to additive manufacturing, I open to the participants.
Thank you, sir. Thank you for your deep information about additive manufacturing techniques in recent trends. Dear participants, if you have any queries, you can ask the questions with the resource person. Or you can put the queries in the chat box also.
Okay, thank you, sir. Here, actually, I'm open to the collaboration. Here, it's my contact. You can take it in metal or polymer or whatever the additive based. We can collaborate. If any queries, I'm willing to ask.
Yes, sir, we can share resource person details to all the participants.
Sure, sir. Sure.
Yes.
Second, thank you. Thank you for giving me these wonderful opportunities. Thank you. Thank you, Manivel, sir.
Yes, sir. Thank you, sir. Thank you.
I can see only thank you in the chat box, not any queries. Okay, sir, I am open to collaboration. Okay, I have shared my contact, which you can contact at any time. It's any additive related or superalloy related or anything materials needed, where it is available, where we can get it, what is the cost related, everything we can collaborate in publication point of view or any. Even if you want to see any metal additive related missions also, if you want to see and you have to explore this to your students community, we are I'm really will, helpful to do that also.
Thank you. Thank you, sir. Thanks for your valuable information.
Thank you, sir. Thank you.
Again, sir, thank you so much.
Okay, sir.
We will start with the next session.
Sure, sir.
The resource person is waiting here.
Okay, sir.
Thank you so much. Dear professors and participants, we will share the second session, end of the second session, feedback link for the both session 1 and 2. Because due to time constraint, we will start the next session now within a few minutes.